So welcome to CS235. This is lecture 5. Today's topic is belts. So a few administrative things. I'm going to start sending out individual emails, but I need PRL safety training to be completed. How many of you have not done that? Show of hands. You've all done PRL safety training. Quite impressive. Okay.
Do you want some confirmation from us? You want like, I did PRL?
That'd be nice if I could just get an email, and then if anyone cuts their finger off, I can say, hey, they had PRL training. A few of you still owe me checks. And show of hands, how many people have not submitted their Clark Center safety forms to me?
I sent you like confirmation email, but you said you need the right PDF.
Yeah.
Okay.
Okay. So if I've sent,
What if I sent it to you? But
I got yours.
Okay.
So if I sent you back a note saying almost, please try again with something slightly different, please send me it. Let's do questions about Lab 1, etc. at the end of class. One quick note, and I'll explain more later. If you're having trouble sanding your shafts, it's taking forever. You probably are using too fine of a grit of sandpaper. You want 400 grit for these shafts. And if you're frustrated that you sand it and you stick it and it doesn't fit and you keep doing this repeatedly, it's probably because you're not cooling the shaft. There's a coefficient of thermal expansion, and if you sand it and it turns red hot and then you immediately jam it in the bearing, it's bigger than it really is at room temperature. So dip it in water, dry it off, and then try it. We solved a half an hour problem in 30 seconds by dipping it in water last night, and then it magically fit. Okay, so enough of that. I need each of you to get up in a line. Only those who are actually officially enrolled, because I have exactly the right number of things. You're going to get 1 shred of belt, 2 pinches of pulley, 1 of these little metal or plastic pulleys, 1 belt, and 2 paper clips. So everybody up who's actually officially enrolled. 1 of those. And I need every single one of these components back today, please. Because these are going in your lab 2, and so if you keep it, then you can't do lab 2.
Well, we can keep it and then use it in the
I have to use these later.
Doesn't matter which one?
Nope.
2 paper.
2 paper clips, 1 belt, 2 of these.
These?
Yep.
Anyone?
Yep. Any one of those pulleys is fine. It's just an example to show you what they look like. 2 paper clips. Don't forget the paper clips. That's fun.
Just one of these?
Yeah. And yep.
So one of these.
1 of those. 2 of these. 1 of these. 1 of those, and 2 paper clips. Uh-huh.
Okay, so what are these?
Yeah. 1 of these. 1 of these.
There's also
2 of these. 1 of these. 2 paper clips.
parked just right outside the white lines, and he pushes everybody else out.
2 of those.
And one of these.
2 of these.
2.
1 of these. And 1 of each of these, and 2 paper clips.
One of these, right?
Uh-huh. And again, please, even if you have to leave early or perhaps mid-lecture, please bring all of your stuff back. I'm not going to be upset. Just place them in this bin. If I don't get them back, I didn't order enough, so someone won't be doing lab 2.
Right, and then we pick one of these.
1 of those, 1 of these,
One of those. One of these.
and 2 paper clips.
Okay.
And this is only if you're officially enrolled, because I only have just enough for the people in the class.
Which one?
Any of those, and 1 of these. Yep. These are just samples, so you see what they look like. 2 paper clips, 1 belt, and 1 pulley.
I mean, they'd be talking your names every time. Sometimes you get them and they go off on a tangent and ask you something else. And like, then you stare at them and they go, that's a little question.
Okay, please be very careful with these belts. I will be going over in lecture how to kill them and how not to. So for now, don't kill them until I tell you how not to.
1 or 2?
2.
2. That's 1 for you. 2 paper clips.
How's it going?
Okay, what's going on over
2
here?
of these, 1 of those, 1 of these. Doesn't matter which one.
Oh, it doesn't matter?
Nope.
Oh, it doesn't. Well, I'm a happy guy.
Whichever you like.
paper clips that all
2 paper clips.
do with each other.
Stud lab 2 or no?
No. That would be sadistic.
Yep.
These are not lab 2. I didn't mean to frighten anyone.
Rough.
Okay, 1 of these, 1 of these, 1 of those, and 2 paper clips. So, does everyone have 1 shred of belt, 2 little wood pulleys, 2 paper clips, 1 belt, and 1 assorted pulley? If not, please come and remedy that.
Nothing are really hard.
2 wood things, 2 paper clips, 1 of everything else. Okay, so we're going to put this up for a sec. And today's going to be fast because we have a lot to get through. Again, belts are one of those Mariana Trench type topics. We're only going to be scuba diving today. Not doing any Richard Branson stuff. Okay, so everybody take the black belt. Karate chop something. Okay, so that's a belt. That specifically is a timing belt. And go ahead and on a flat surface take the 2 wooden pulleys and put both of them inside and stretch it till it's a little bit tight, just so that the sides are flat, top and bottom. Okay. Now you're probably going to want to spread the 2 of them open with your fingers on one hand, and then with your other hand you can rotate one of the pulleys, and you will see that, not surprisingly, they rotate. Okay. So just that is a belt. I figured that would be better than drawing something. So, see, I have 2 pulleys, 1 belt, and when I rotate one, the other rotates. Cool. What is the driving mechanism here? What physical something is making those pulleys drive? Friction. Just because it has teeth doesn't mean it's not friction. It just has a very, very high coefficient of friction. If I have 2 gears, and now I separate them, so these are gears, they have to be in contact. And now I put one of them over here. It's basically like a gear. And then I put a pulley, a belt all the way around. This does not have to be a belt. This idea right here, think of this as an abstraction. This is a very separated drive transmission that uses some type of string here, and there are many strings we could use. Bike chain, belt, cable, and by this I mean like a steel cable, string of pearls. Everybody knows a necklace with pearls. You can actually, anybody here heard of Hansen Medical? They make a little heart surgery robot that worms its way through your veins and into your heart and does ablation for atrial fibrillation. And it uses a string of pearls instead of a cable or a belt. It's very, very rare, but they're used. Anybody seen we don't have them here. Often you'll see these on, what are they called? The window blinds. You know how you'll raise and lower the window blinds? That's a string of pearls, and they have a special little pulley designed just for that. So this is why I'm saying this is an abstraction. If we had to come up with theory for each and every one of these, it'd be sort of a pain, right? They're all exactly the same. We have 2 circles, one driving, the other being driven, and some type of string in between them, and every single one of them relies on friction. Today, we're only talking about belts. Probably 2 lectures from now we'll talk about cables. Much of this is the same, but cables, they're a deeper hole. So there are different types of belts. The type in your hand is called a timing belt. It also might be called an indexing belt or a toothed belt. And those are sort of, in terms of industry, they're the more complicated type. Often what you'll have instead Can you see above this? I'm assuming, unless anyone's on the knees. Okay. Let's look at the cross profile. This is just called a flat belt. Okay. All it is the rectangular cross section. This is basically a rubber band, a really nice rubber band with some stuff inside it that makes it stronger. It doesn't have to be on a flat profile. you can also put it on a bent one. This is, I believe it's called crowned. They use these a lot in automation. This is basically to keep it from wandering off the pulley, but it's still essentially just a flat belt. Okay? So now, if I drew this, this is the belt, and I'm slicing this cross section here. That's what we're looking at. Okay? We could also have a round belt. Okay, that's very simple. These don't get used that often. When they are used, I believe this is a 60-degree, and it basically wedges itself in there. So again, this is that cross section. Everybody see that? This is our belt, and this is just the cross section right here. Okay, our timing belt. And then, depending on which cross section you're looking at, I'll get back to this later. This is sort of the flat section of our belt, and this is the teeth. And I'll explain these later. These are the tensile members. And then the next one is, looking at this, what do you think the next logical one might be? These are everywhere in your car.
Right here.
Almost. V. Or, I guess I don't need to quote a letter of the alphabet, but V. And so if that is the wedge, then and actually normally they clip off this bottom here. Okay. These are super common, and the way this works is it wedges deep in there. So if you were, you know, drawing this in a, another way, okay, so so it wraps around the pulley that way, and so here, let me shade in. These are the cut ends. Everybody see this? It wedges very deeply in here. You have a lot of contact area there, and you have extremely. These are power belts. Again, these are in your cars. These are in your drill presses. The drill presses everybody's using for Lab 1. If you look inside, this is what's in there. This is in our mill lathe. Very common, very powerful, very not precise. Very not precise. All of these can slip. Say that if this is my pulley here, and this is my second pulley, and this is theta 2, and this is theta 1, and I'm just going to twist this and expect this to twist the exact same amount. If I just, I don't know, throw a wrench in here so this can't move, it's just going to start slipping, right? And if I'm not sensing that, I'll have no clue where I am in the end. So the solution is this timing belt with the teeth. Because assuming you don't actually rip the damn thing apart, so you don't rip off the teeth or you don't start jumping teeth, etc., it can only slip by a very tiny amount, that being the backlash of the belt. So that's why they're also called indexing, because you do it for very precise motion where you index the motion and you cannot slip. You can't lose count.
What's it called, timing?
It's called timing because if you use these in a car, they're so precise that you can time things together. So you could have like a camshaft with a belt connected to things that will time various things moving at the proper timing.
Within the 60-degree thing,
I don't know, imperial.
what was it about?
Oh, if you're looking, does everybody see the 60-degree thing? It's just the angle here. If we were to imagine taking a cylinder, and if we look at it,
The circle is a cross section of.
this is what the pulley looks like. Okay, so this is the central axis, and these are the flanges. See that? So this is a circle if we look at it like this. But does everyone see the V belt goes in here and grips it? Okay. Okay, so basically, as far as I can tell, and this is my sort of personal opinion, the two types of things you're going to want to do with a belt are either transfer a hell of a lot of power, in which case you're going to do like a V belt probably, or you're trying to transmit precise motion, in which case you're going to use a timing belt. We're doing robotics. Almost all the time we use a timing belt, it's because it's precise motion. We're trying to take motion off of a motor and turn the gripper or the wrist or the shoulder of a robot arm. let's go over some quick terminology. I'm going to erase this. A lot of the terminology for gears is the exact same for belts, but there are some differences. So this is the bottom of our belt. Okay, and we can pick some identical point between the teeth. This is called the pitch, P. Okay, and if we extrude this into the board, okay, like that, and blah blah, some more lines. This is the belt width. There's also an imaginary line somewhere around here. It's not so imaginary. This is called the pitch line. Now, everybody take your shred of belt, and I want you to look Can everybody see that? See the little silver dots? Look at the little silver dots on the end of your shred of belt. See those? That's stainless steel. So those are some type of rubber belt. I don't particularly remember the specific type of rubber. And it's coating stainless steel cables. Can everyone see that on your little shred of belt? Okay? And if you actually look in between the teeth, you can see the lines. It's really thin stainless steel. So, I don't know if you can see the little lines in between the teeth there. So, before we get back to this, when you talk about a belt's material, there are two types of material. The material is this rubbery stuff, like the tooth and the backing. And this is going to be some type of soft rubber. Let's see what we got here. There's a list. So these might be urethane, polyurethane, rubber, neoprene, something soft. Along here on this pitch line is called the tensile member. Belts only work in what? Tension. You can't push on limp spaghetti. You can if it's raw, but it'll fracture.
That was another name for the pitch line?
No, it's not. This is what is right there. So, yeah, give me 1 second. I'll explain that. So basically, belts only work in tension, so they need tensile members. Because if you took out the stainless steel cable, it would basically be a glorified rubber band. It would just stretch and then break. So these teeth are what keep you from losing count, from actually slipping. They have positive engagement with the pulley. This tensile member along the pitch line is what actually keeps it from stretching and breaking in half. Now, is everyone here familiar with, so let me draw this head on. So these little dark circles here, those are the tensile members. Okay? They run all the way around the belt continuously. Is everyone familiar with a cantilevered beam? If I take a beam here and I ground it, and then I press here, half this beam is going to be in tension and half of it's going to be in compression. Which side is this? Compression, and this is? Okay, and what about on this dashed line? Neutral axis. This may seem far-fetched, but it all ties together. So this dashed line here is the neutral axis. And this is a standard cantilevered beam. So, when you push down on a cantilevered beam, and you could even take your pin and just kind of torque it, the bottom half is under compression because the material is trying to get out of the way. and the top is being stretched because you're bending it. So we're making a smaller circle here and a bigger circle here. And then this dashed line in the middle, nothing's happening. There's no stress there. When we wrap a belt around a pulley, say we took this and we wrapped it this way. This side would be compression, this side would be tension, and this pitch line is the neutral axis. Now, it's very important that it's the neutral axis, because if it were not, we would be fatiguing it, we would break it. We'll talk about that later. But so the other thing that this pitch line is very important for is when you buy a belt, unlike a gear, there's no diameter. You don't buy a pitch diameter belt. You buy a pitch length. Okay, so in my example, if I have two pulleys like that, this is the pitch length. That entire length here, and that length is drawn along the pitch line. Okay, so say I put two pulleys here in green. By the way, can everyone see this? Am I in the way? Is anything else in the way? Everybody see this right here? Okay. What's the name for the pitch line? Oh, sorry. This is the pitch line on the belt. What's the name of this green circle corresponding on the pulley? Pitch circle. And its diameter is the pitch diameter. So this pitch line is like super useful, right? Because that's where we put our tensile members so that it doesn't stretch and break. It's our mathematical way of calculating where the belt is going to intersect on our timing belt pulley. And it's also how we measure this overall length of our belt. By the way, if you buy a pulley, they say, okay, cool, what's the number of grooves you want? When you buy a bolt, for a pulley they say, what's the number of teeth you want? When you buy a belt, they say, what's the number of grooves? I don't know why they do that, but you always want to spec your timing belt pulley and your timing belt in pitch diameter and pitch length. Just work in millimeters. If you're doing number of teeth, it just gets really confusing. Okay, and just as with the rack and pinion, this linear pitch here has to match the arc length pitch here. So if I have two teeth, that distance P has to be exactly the same as the linear distance P there. Everybody take your pulley and your belt and kind of watch as you rotate. You can use one to make it easier. As you rotate, you will see you have that linear distance and it perfectly starts curving down into the teeth. If your pitch was mismatched, that would not happen. They would jam.
So essentially the number of grooves on the belt would be equal to the number of teeth on the gear?
There's probably a plus or a minus one in there.
Okay. But like the pitch has.
So if you decide that you have, basically you're going to figure out, I want this type of belt and I want this size diameter, so you look up your pulley and then you're going to measure the arc length you want or the length of the belt in SolidWorks. That's how you pick your belt. Don't worry about number of teeth.
For a longer tray, we don't want the number of teeth to be equal to number of grooves, right? Because the belt is longer.
Yeah.
So can you even work from that?
No. Just disregard teeth and grooves. I don't know why people work in it. I don't even know why they list it. I never work in that. I always work in pitch and then pitch diameter and pitch length. Okay. That is a single-sided belt. Imagine it had teeth on both sides. That would be a double-sided belt. That's all you're going to get from a belt. There are no triple-sided belts. The reason why you might want a double-sided belt imagine we have a pulley here and our belt comes like this and we want to spin this pulley here. Okay? Our belt teeth are like this here and our belt teeth are like this here. So we have to have teeth on this side here and on this side here. You see that? So that's why you want a double-sided belt. Most of the time you use single. Okay, that is called a closed belt. If you have something with a free end, this is called open-ended. You buy them in spools. So those closed-ended belts are continuous loop, and you buy them according to some pitch length. This you buy a spool of, you cut how much you need, and then you terminate the ends. This is more flexible, but then you have to terminate the ends. So basically the way you terminate the ends is you just clamp them against something. You don't really want to crush the teeth. So normally if you are clamping it, they actually sell these little, you can either laser cut your own, or they actually sell these things on Masumi. I don't remember what they're called, but they're for terminating belts. And basically if this is your belt, then it will basically have the corresponding grooves in it, and it'll be made out of metal, and you'll clamp it down, and that way you've got the added shear force of these teeth.
What is this again?
This is for clamping, aka terminating an open-ended belt.
So you're taking the two sides and clamping them?
I'm taking this belt here and say this right here is whatever I want to clamp it to. Say this is a piece of steel right here, and this is my belt, and it goes off that way. And I want it to be rigidly held here. I take this little piece of metal that's basically a metal version of that belt, and I clamp it down here, and it can't move.
You're not making a circle.
No. I mean, essentially, take your two fingers and just squish rigidly the end of that little nubbin. If your fingers were made out of metal, that's what we're doing. Terminating is just holding on to the end of the belt. And there are good ways and bad ways of holding on to the end of the belt. If we literally took two flat plates and just squished the belt, then it would just deform the teeth, and we wouldn't get much friction. If we then fit the teeth of, now imagine that your little fingers could fit into the grooves in between the teeth, that'd be much higher friction. So that's why when you terminate a timing belt, if it's open-ended, you want to stick things into those teeth to get the highest friction that you can.
So this allows you to basically attach these open-ended timing belts to any type of branding material.
Exactly. Exactly.
Would you be able to make a closed loop belt with one of these open-ended ones?
That's my next point. Thank you. No. Well, sort of. Let me draw something. I'm not making anyone dizzy by flitting around the board yet. Okay. So say we have a pulley, and I want to drive it from another pulley over here. Okay? And in green, I'll have a belt. Now, I could do two things. I could take my belt and go all the way around, and in SolidWorks, I'll make this the pitch diameter of the one, pitch diameter of the second. I will measure this. I got my pitch length, and I order my pitch length. Cool. Well, maybe, I don't know, there's a 3-week back order lead time on that, which happened to me ordering stuff for your lab too. That's why you have the specific belts you have, is because those are the only ones that they had in stock. Instead, I could take just a spool, and I could cut it. And I could terminate there, and I could terminate there. For limited motion, this is totally fine. Basically, until this comes to that point, the tangent, it doesn't matter. It's the same thing. Now, if I want to go beyond that and do multiple turns, I'm screwed, right? Does everybody see that? Everybody got that? So this is really convenient, especially in laser cutting. You can laser cut the little tooth profile and just stuff it in there, and it will not come out. It's super strong. But if you wanted instead to do multiple rotations, And you're just going to say, let's zoom in here. I'll put one here, one end here. I don't know, I'll super glue that or I'll clamp it. There's no way of doing this cleanly so that it will fit in the grooves of the timing pulley. It's just not going to work. Now there are exceptions to this, not for belts, but for cables. I think some ski lifts have continuous type ones that they took open-ended cables and they spliced them. But there literally have been dissertations on how to splice belts and how to splice cables. Just don't do it. There's no reason.
Do belts also have tolerance?
It's an excellent question. I'm sure they do. I don't know what they are or how they work. All right, let's talk about this tensile member for a sec. The tensile member is where? Pitch line. All right. So imagine it just running through like that. Variety of materials that you'll see include, I just went to Stock Drive and picked out the belt that we were looking at, and they had some different options. We could use fiberglass, polyester, stainless steel, Kevlar, the stuff they make bulletproof vests from. These are all super stiff. I don't know about polyester. I've never bought one of those. Fiberglass, Kevlar, stainless steel, they're all wonderful materials. I'm sure if you did this for a living, like where all you did was build things with belts, you'd get really good at knowing the pros and cons of them. They're super stiff. I don't see much of a difference. I like to go with stainless steel when I can, just because I've used them, they work well. And basically the stiffness of that is setting the overall stretchiness of your belt. You're going to have other problems before you run into the stretchiness of the belt. As in, if you're worried about, going back to that example, if you have one pulley and then a second pulley, and tracking the two, theta 2 and theta 1, make sure they match. The backlash and all the tooth deformation is going to kill you before this springiness here. Don't even worry about that. Okay. Belt walk. Take the black timing belt you've got and put it along one of the pulleys. And then notice that you can slide that belt actually along the axis of the pulley. So go ahead and do that. You can just slide it right off, right? So say we had two pulleys and a belt. Okay. What is to keep this belt from coming straight off at the board off the pulleys? Nothing. It will do that. It's called belt walk. Now everybody pick up the little pulley that you've got, the metal one or plastic. Okay. That has flanges. Flanges are those very thin little metal things on either side of the teeth. That is what keeps a belt from walking off of the pulley. So I'm going to draw sort of a side section. Okay, so just a little bit of pulley terminology. These are the flanges. If you're using a timing belt, you really do need them. This is the hub, just like with the gear. This is the bore. This is the teeth. And the three ways here are, let's write them down. What's the simplest way? Some type of fit.
Press fit.
Press fit. What's the next one? No, that wouldn't drive anything. Clamp. And what's the third one? Set screw. Those are the three ways. There's actually another way, which is you usually don't see them for gears, but you do see them for pulleys. Imagine we looked at this face on. So it's just a circle, and this is the bore. Sometimes they'll give you threaded holes, and you can bolt directly into it. Masumi has a lot of these. They're really nice. They're like big, honking, like this size pulleys. I don't know what those are called, so I call them, just myself, through face screws, because you screw directly into their face there. So those flanges prevent it from walking. If we have two pulleys, do you need two? If you have one belt system, so two pulleys, do you need two sets of flanges or not? The answer is I don't know. There does not seem to be consensus on this. Some people say, well, if one of them's big, you put the flanges on the little one. I don't know. I have built many belt systems with one little one and one big one. I've put the flanges both only on the big one and then only on the little one. They all work the same. The belt never came off. Me personally, as long as you have one pulley with flanges, I don't care about the other one. Yep?
What if you, say for example, you have a two-pulley system and they're kind of offset so that your belt is driving at an angle?
Yes.
What does that do to your belt?
Sure. We can go over that now. These are all points, but I don't mind jumping around. So let me make sure I get your meaning. So, I take this parallel belt and I twist it, right? Because if I have a pulley around this axis, like this, it's straight. And now say I rotate the axis, my belt's going to be curved, right? Twisted. You can do that in a limited amount. I wanted to show you a demo. When I first got here to Stanford, I built a 90-degree belt drive where it took a shaft here and a shaft here and connected them with a single belt, and it twisted all over the place. It was cool. It lasted 8 hours of cycling before it ripped. But actually, if you go to the hospital, to the emergency room, and turn left, you'll see a bunch of vending machines. And there's a little Pepsi bottle, or Pepsi or Coke dispenser. If you look up in there, they have a belt that does this. It does like 2 90-degree turns. It's really cool. And it's an open-ended belt, I think, and so they have to terminate it, and it does 2 90-degree bends. So you can do this to a limited amount. Now, here's a trick for twisting belts. Which is easier on the belt? I'm going to twist 90 degrees here, or I'm going to twist 90 degrees here. Length. If you want to twist something, and this is the same thing for a steel cable that we'll get to in a couple weeks, the bigger the length you have, the better. At infinity, you can't even tell they're twisted, basically. So basically, you want as big. This works, this does not. And if you just do not do this in your own hands, trust me, you can just feel that this does not want to twist. Or you could even take your little nubbin and take the very ends and see how hard it is to twist. And now, just as close as your fingers can get, twist it. Fingers right next to each other, and it just will not twist.
I was meaning more like if you drove a belt like slanted, like not twisted, but like.
Oh, not even on, like directly on it?
Yeah. Like,
okay, so let me draw what I think you mean. I think the answer is that's not good. Alright, so if this is our pulley, right, then you're saying what happens if our belt is like that? At angles and it's not flat on the surface?
something for that green diagram, if you had like 2 diagonal lines going along it, or
Like that?
like across the pulley, like from that top.
Like that?
Yeah. Something like that.
You'll rub on the flanges. So anything that gives a force along the axial direction will lead to the belt walking in that axial direction, and then it will rub on the flanges. What will happen? I don't know. I've never done that. Eventually, I mean, these are metal flanges and it's a rubber belt. Eventually it's going to rub the rubber away, and then it's going to start eating at the tensile member, and at some point it's just going to crack. So I wouldn't do that. You know, you can get away with it for a little bit, but ultimately it'll rip your belt.
Just the degree at which you rotate it also depends on until it like falls off. Does it also depend on the speed of the belt?
Yeah. Please do not twist these belts. I see some of you twisting them. Please don't do that. It'll break the belt. Okay. So we did that. Yeah, basically when you buy these, typically cheap ones are plastic. They'll have like a metal bore. Some of you have ones. It'll be like an aluminum central bore and then plastic teeth. More expensive it's aluminum, more expensive still is steel. Normally you don't get steel pulleys unless they're just gigantic. Okay, so let me draw this line here a little better. I want you all to take your 2 wooden pulleys with the belt in between them, and I do not want you to have it tensioned. I want it floppy. Okay, now rotate one of them. And notice that not much happens. Does that feel right? Do you think that'll transmit a lot of torque? Or position something precisely? No. Belts work in tension. You have to pre-tension them. So, if I have a pulley here, and a pulley here, and a blue cable in between, belt, I have to pull with a tension T on that belt. Now, if I ground this one and I twist this pulley, I'm going to be basically increasing the tension here and decreasing it here. Okay? So this will be minus some delta T and plus some delta T. That's why you have to, part of why you have to pre-tension your belt. And for those of you who are, I can tell by your faces, are having trouble believing me, I have an example. So I don't remember the student's name. I probably wasn't born yet. This was Dr. Salisbury's master's student's dissertation at, or master's thesis at MIT. I don't remember his name, but he's a cool guy. These are springs. This is a cable drive. Just imagine for now it's a belt instead. These are two little springs. Can people see it from here, or should I put it on the camera? Okay. Now I'm rotating back and forth. Anyone see what the springs are doing? They're compressing and stretching and compressing and stressing. And notice they're cycling. I'm reversing rotation, and each spring is alternating between compression and tension. So let me put this on the camera so we capture it. Okay. So I'm going to ground one of these. See that compressing and stretching the springs? That's inherent in a belt or cable drive. When you need to drive a load with that belt or cable, it's going to change the tension on the two sides of your pulley system. One of them is going to get tighter, the other is going to get slack. Let me ask you just a dumb question. Why do I have two sides to a pulley? You know what? I'm tired of having two-sided pulleys. I'm going to start a revolution. It's going to be one-sided pulleys only. So I'm going to terminate here and draw my cable like this. And which direction can I rotate this? This way. Okay. Can I rotate that way? Alright. So that's why I have to have this side. And that's why both sides, I have to stretch them so I get tension on both of them. Now, say I twist this until I add 10 pounds of, I made the cardinal sin, 10 newtons here. I almost used imperial. And I subtract 10 newtons here, and this goes down to 0. 0 here, and say 10 newtons here. What happens? It goes slack. There's nothing inherently wrong with going slack, except that your belt may very well pop off of your pulley. If it goes too slack, it will have enough room where it can just lift off of the flanges and you're screwed. So this is always the issue with cables and belts, is if you ever go slack, you might just pop right out of the flanges. Just take your belts, take your pulleys inside your belts and stretch them, and see how hard it is for that belt to come off. Now move them together so it's slack, and see how easy it pops out. That's what happens. So, if you know you're going to need 10 newtons here, then what should our pretension be? At least 10 newtons. Much more than that, probably. You always pretension more. So, given these two pulleys, and is everyone clear on why we have to tension these belts? Given these two pulleys, let's say I'm going to take this shaft and fix it. Now what I mean is I'm not moving that shaft. It's free to rotate. And this is okay. So this is fixed. I'm not moving it. What's the simplest way to tension the system? Pull them apart. Just what you're doing in your hands, right? So whatever this distance is, you expand it. That will tension it. Okay? What's the other way? Say now I've grounded, I have fixed both shafts. They're spinning quickly in the machine, and I can't drag this one, and I can't drag this one. Now, how do I tension them?
Shorten the belt.
I can't shorten the belt. Say that this is a closed belt, and I ordered it, and I'm stuck with the belt I've got. Add a third pulley. So what I could do is I could put a pulley right here, and then I could make the belt go that way. Everybody see that? Okay. Now, you guys are awesome.
But you can put it on the inside.
There are bunches of topics here. So, which direction? This one or the teeth on in this case? This one or this one? In terms of belt teeth. Which side? This way, okay? Belt teeth are this way. So this side is flat. So I don't need this to have teeth. Everybody see that? No teeth. By the way, anybody know what this is called? Other than a belt tensioner? Idler. Now, someone else, I believe, suggested that we do the following. Which is we have our two pulleys here. Okay? And we stretch it that way with an idler. This was someone's suggestion, right? Okay. Which side of the belt? This one or the teeth on? Left or right? Right. Okay. So then does this be flat or toothed? Toothed. So this is a toothed idler. If you had, now let me just tell you something. Those little ball bearings that you've been using for Lab 1, if you took away the flanges, they are perfect idlers. You could also stick two of them together with the flanges out and they make perfect idlers. They're super strong, they're super cheap, they're really nice. So, if you had to either machine or buy a toothed idler or take two 50-cent bearings and do this, which would you rather do? You'd rather do this. Now, I have also used flat idlers on that side where it needed to be toothed. It's very tricky business. What happens is every time a tooth, so a tooth on this side and a tooth on this side, we track it through. It's not compressed here, it is compressed here, and it's not compressed here. So it sounds kind of like ka-conk, 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 only really fast. It introduces vibrations into your system. That's bad. And we'll talk a little bit later about what that means. So if you mismatch and you use a flat idler on the tooth side of the belt, you can do it. It will turn, it will work. If the ratio of the size of the gear tooth to the diameter of that is particularly large, as in its tiny little teeth and a huge idler, you probably won't even notice it. But if you get that ratio wrong, it's going to be terrible.
Use the flange idler and no flanges on the actual windows.
No, that would be a bad idea. The idlers, well, I guess you could. Part of it depends on when you buy this stuff, what's precision and what's not. The idlers tend, depending on how you do it, to not be good for that. Okay, so now on this one, there are two ways that we could constrain the motion. We could either put a slot this way, and then we move it back and forth linear. Okay, so that would be linear. Or, let's we can rotate. Everybody see this? Say this is a bar with an idler on the end, and we rotate down into the belt. Everybody see that? So we can either rotate into it or slide it linearly. Both work really well depending on the situation. I'm sure you'll develop personal preferences for that. I've used them both. Oh, well, what's the last and least good way of doing of tensioning a belt? The perfect fit. I know exactly how far apart these are in the pitch diameters and the pitch length from SolidWorks, and I order the belt and I assemble it, and maybe, just maybe it will work. It probably won't, but maybe it will. I have done that. This is what everyone who starts using belts does, is they design for exactly the pitch length they need, and they assemble it, and it sort of works. That's what I did. This was the first thing I did at Stanford. You can see here, see there's a giant pulley and a little pulley and a belt and nothing else. Should show on the camera. So I sized it perfectly. I assembled it. It did not work. So I laser cut like 4 different, slightly different hole spacings, and I picked the one that felt right. That is a terrible, terrible way of doing things.
I think it's zoomed in.
Oh God.
I mean, on the computer.
Doubtful, because I don't know how to do that.
It's zoomed 300% at the bottom.
Oh, well, you're very correct. I'm just going to move that until we... really? That sucks.
There's a minus magnifying glass.
All right, somebody tell me where it is, because I can't see.
Right.
There? Oh, God. Worse.
No, try the 135.
Okay, let's try that one. Let's see if... There we go. Okay. Now you can see. So this is the little one. This is the little pulley. This is the big one. This is the belt, and there's absolutely nothing in between it, and it works really well. It's worked for years. But please don't do this. It pains me. Pains me to see this happen.
How did you even mount it?
Exactly. It's terrible. There's this order of operations thing where you put it on the big one first, and then you shimmy on the little timing pulley, and it's just a pain in the ass. It took like 20 minutes. I mean, if you've designed your belt system properly, it should take at max 30 seconds to install and tension it. Yep.
So how about making a, instead of having the idler, allowing the top gear to slide up and down? Is that okay too, or no?
Say it one last time.
So in the right side, you have the idler moving left and right.
Yep.
So let's say you were to take away the idler and just have the top gear slide up and down.
That'd be fine. Yeah, you do that too. So let me tell you why you might, what the different issues are. With an idler, you don't have to move these shafts. Often you can't move the main shafts. One of them's a motor. Maybe it's next to something. Maybe this is next to something. It's much easier to move a little idler versus something beefier. Also, and now this is the demo. I apologize. This is the part of the lecture where you're going to be like, what the hell is he doing? And then 20 minutes later, you're like, ah, he is crazy. Okay, so this is a base. This is related to mechanical engineering. This is wave theory. Each one of these strings can be thought of as a belt. It's under tension, and I can pluck it, and I hear it. It's at its resonant frequency. Okay, and the issue is all mechanical systems have resonant frequencies, including belts and cables. This literally is a cable. You could take a bass guitar string and tie it around a capstan and use it exactly the same way as just a stainless steel cable in my haptic device. Okay, it's literally the same thing with the exception of the way they make this cable, but it's a steel cable. If I try to operate a robot above this frequency, I'm going to excite this. And then I'm going to hear my transmission. Now, two things are going to happen. Either it's going to annoy the people who are using it or sitting next to you because they're going to hear this constantly, or it's going to cause your system to go unstable and it's going to decable itself. And I was thinking back today about, okay, well, when have I seen this happen? When I first got here, there was a new haptic device. It was a 6 degree of freedom 1, and they had a really long span of cable with a giant, massive spring in the middle, and it had a low resonant frequency. They were trying to operate above it. It hit the resonant frequency, it went unstable, and ripped itself to shreds. Okay, now this is pretty low. Okay, Say that I decided, oh, I'm actually going to go lower. Let's do the high string. That's my cable. And I want to operate down here in terms of the frequencies I'm working at. All right? I'm never going to get near here, ever. Except when? Except that. When your robot gets kicked, or it hits an end stop, basically when it gives an impulse, it excites the spectra. Right? The step function is terrible for robots. It's the worst case because you are exciting across the entire spectrum. Even if you're operating at 10 hertz, if you kick your robot or your robot hits a rigid end stop or someone throws a gear in there, it's going to see all of those frequencies excited. And if you excite a resonant frequency and don't have any way of getting rid of it, of dampening it out, it's going to rip your device apart. Okay, so we know about the fact that we have resonant frequencies in our belts and in our cables, and that this could possibly be bad because our robots will rip themselves apart. So let's write down what the equation is. So the frequency F of that is 1 over 2L square root of T over mu. What's L? That's length. I'm not even going to write that one down. What's T? That's tension. What's mu? Mu is linear density. And I suppose for the L challenge, we'll just make that length. Okay. So, let's play with the bass a little bit.
What's the resonant frequency of the...
This is the fundamental harmonic.
Is that the total length or the length between, like, where it leaves the tooth and enters another one? It's the
Free length.
Of the bell.
It's this.
Okay.
It's not the pitch between the teeth. It's this free length here. Okay? So, thank you. Let's draw that. So in this case, we're talking about, this is L. Okay?
What did he give us for tension and linear density?
Tension will be force. This will be millimeters. And this is mass per unit length. So like kilogram per meter. Oh, does everyone know what linear density is? It means if I take a string and I chop off 1 meter, how much does that weigh? So that's in kilogram per meter, I think. Someone correct me if I'm incorrect. Okay. Is everyone familiar? So the first thing is, let's just make sure this equation. This is the tuning, right? This is a worm gear, by the way, for any of those who are interested. It's a worm with a helical worm gear on it. So I'm going to just stretch this and increase the tension. Okay, well that's good. The tension increased and the frequency went up. Math, the physics held. Okay, these are frets. Now when I press one of these frets, I'm what? Decreasing the length. So it didn't sound good, but it worked. So every time I do a lesser length, the frequency goes up. Okay, cool. So now that we know that we can increase the tension and the frequency goes up, and we can decrease the length and the frequency goes up, and we want to boost that resonant frequency as high as possible to give ourselves as much range away from the frequency we're operating at as possible, we have two options basically of tensioning. We can either take these two and spread them. Let me draw that again. And I'm just going to take this and move it. Or I can put an idler in the middle. Which of these assume approximately the same separation? I mean, when we talk about moving that, we're talking about like 1/4 of a millimeter. So these are basically the same separation L. And this is L plus epsilon. That was a nasty epsilon. Which one of these is going to have a higher frequency on one of the sides? This one. That idler reduces that free length to that and that instead of this. Now what we could do, what would be awesome, is if we had one fixed idler and one slotted. Okay? So now we come like this. So this is fixed. This isn't moving in terms of its distance, and this we slide to change the distance. So now we've got this little distance here, and it boosts our resonant frequency from that free length as opposed to here, and we tension it just the same. Does everyone see that? That's important. It turns out this is a way easier way of doing it. You don't want to mess with this. I mean, you can, and I've done it, and it's in my dissertation, but this is a lot cleaner. Now, just real quick, you can use ball bearings for this. I've used it many times. There's another thing. I can't buy them for all of you because they're pretty expensive, but these are called track rollers. Track, like running real fast, and then rollers. Let me show you what they are. Okay. Everybody see that? So this is a needle bearing on a stick. It's a special type of bearing, and it comes with a little bolt on it, and I can bolt it, and then basically this little nut allows me to slide it, and then I tighten it, and I'm done. It's like a 1 part count way of tensioning a belt. It's really cool.
How significant are the losses with just the increased friction?
I don't know. Excellent question. I have no clue. Usually belts are around 90-something, 94 to 96% in terms of efficiency. I haven't seen any specifications in terms of the number of idlers, but that's a really good question. And when we get back to talking about cables in a couple weeks, it will be a huge question. This is another one. This is an idler that's hollow, and you put a shaft through it. So you can either get them with shafts on the left, or your left, or without shafts. Sometimes the shaft's called a stem, so it'll be called a track roller with a stem.
Do you usually have to lubricate
The belt?
anything in the belt? Yeah.
No, don't do that. A lot of lubricants will eat the material on your belt if you pick the wrong one. You don't want to lubricate your belts. So we talked about idlers, using them to reduce the free length and boost the fundamental frequency. Yep.
How do we know if we're tensioning too much? Is that
Excellent. That's my next point. Man, you guys should not be right ahead of me. I need you to teach the class. Yeah, so in robotic prototypes, who cares? You're just going to tension it until it feels good and go. When you're building large devices that are moving heavy loads and have to not fail ever, they calculate what the belt tension should be. They install it to it, and they measure to make sure. There are 2 types of measurement. Basically, one is you put something here and poke it, and it will either measure the force or the deflection. They're just different sides of the same equation. Or they have this thing that pings it and listens to the ringing, and it's an acoustic thing. It's like a microphone, and based on the acoustics, it tells you what the tension is. You buy them, you don't make them. The tension affects the what's it called? There's a special term for this. Working. Let's see. Is it working tension? Okay. I don't remember this. I looked it up months and months ago for a robot I was working on. Basically, when you buy a belt, you want to look in the technical specifications. It will tell you what the max power transmission is. Don't exceed that. It will break. It will also have a working tension. That means it wants you to tension the belt to that tension when you install it. So again, that's kind of more advanced than what we're doing in this class. We're just kind of press it until it feels nice and tight, and then let it be. We're not doing high loads. None of our components will fail. If you're in the field doing this for a living, working tension, don't exceed the max power of or max tensile, ability of the belt, or it'll break. All right. So we did the. So I told you that the tensile member of a belt, at least the ones I like, are stainless steel cables, right? So say I took the exact same amount of stainless steel cable and used just that as a transmission. I didn't use the rubber on the belt. Which one has a lower frequency if I, all other parameters held fixed? It's the belt, because I added the rubber, which increases the mass, which increases the linear density. So if you're looking at cables or belts have a lower frequency. So one might think, hey, this is going to screw me. I'm closer to where I'm working in terms of the frequencies I'm operating at. It actually is better. Does anyone know why? The rubber damps out the transients. It's a low-pass filter. It's beautiful. I was just talking to a colleague about this, and he said, well, I've never had this issue when I was using a belt. And I was thinking, well, the only time I've seen it be an issue is with a cable, and the only answer is that the rubber is damping out that vibration. Belts versus gears. Belts are pretty high efficiency, just like spur gears. Actually, spurs are a little more efficient. Part of the inefficiency of belts is squishing and unsquishing that rubber. It's called hysteretic energy loss. We'll get back to that on Wednesday for friction drives.
Wait, you said that the rubber damps out the transients, and that's for belts versus cables?
Yes, because cables don't have anything soft on them to get rid of that. Remember when we had two gears and I spun one of them and the other one spun the opposite direction? If I turn this belt this direction, which direction does this turn? Same direction. Gears reverse motion when used with gears. Belts do not. You need to remember this. If you get in gear mode and you're like reverse direction, count number of gears or pulleys, it won't work for pulleys. They're different. So basically, if you want to connect two shafts with gears, these would have to be big honking gears. The advantage of belts is you can go huge distances very compactly and also very cheaply. They're often cheaper than gears. Now here's a big problem. Belts load your shafts way worse than gears. Way worse. Because of this pretension, and we're pulling directly against the shafts. So let me show a little video here, if I can find it. Okay, the arrows, the blue arrows, that's the line of force for spur gears. Now see how most of it is a moment, and then you'll have a vertical force on the shaft supporting the shaft. Very little of that is going sideways, or in this case this. It basically has an internal load between the shafts, trying to spread the shafts apart. All of it here is going into crunching these shafts together. Not only are the directions worse for belts versus gears, the loads are higher in terms of we have to pre-tension it. You don't pre-tension gears, you pre-tension belts. So all the times that you're worried about, well, can my bearings handle the loads I'm working at? If it's gears, it's lower. If it's belts, it's way higher. You can't get away with the same misbehavior with belts that you could with gears in terms of bearings. Let's talk about backlash. Belts have backlash just similar to gears in that there has to be an inherent clearance between the tooth and the gap. Now, the difference is when you look up, and they're very hard to find in terms of backlash specifications for belts. You can find them, they have them, but you may have to call a few people to get them. You don't see it, except at very high loads. When you look up the backlash specifications, it's always like something ridiculous, some ridiculous amount of torque. So again, this is my two teeth, and this little gap here is my backlash. Gears are not working in the same way. Like, we have contact right here, okay, in the belt, between the teeth and the pulley. We also have contact here between the teeth. So we basically, at the top of this tooth and the bottom of this groove, and then the sides of both teeth. Does everyone see that? Go ahead and look at the belt on your pulley. And you'll see that the teeth of your pulley are pointing up into the bottom of the groove of your belt. There's friction there. You don't experience this backlash until you've broken all of the friction right here, and then you move that little bit. So keep in mind, when you look at the backlash specification for a belt, if you're using this for indexing, for just like moving a little optical mirror, it doesn't matter. You're not going to be driving at such a load to break all of this friction and then move that little amount. If you're using this for an industrial robot that's building more robots and this weird recursive loop, then this might be an issue, but probably not. Now, they make zero backlash belts. They don't exist. there are very many zeros I can go before I get to 0, and they don't exist. I looked them up. Now the other thing you get is these are not rigid teeth, right? What will happen is if you start moving really hard, you'll deform the tooth, the rubber. So it's called, well, I guess they just call it tooth deformation. The backlash for belts is more complicated than gears because these teeth actually, before they shear off, they bend quite a bit. So you'll get some weird combination of loss of contact, bending the tooth. Don't worry about it unless it's really high loads. For your purposes, they're pretty darn good.
Is that a fatigue issue at all?
Huh?
Is that a fatigue issue at all?
Not on the teeth. Dude, seriously, you were right at my next step. This is amazing. It's like ESP in this room. Okay. Let's talk about failure modes for belts. There are 3 main ones. The nicest one that hopefully you'll get is that there is enough tension and the teeth just skip right out of the pulley, right? So if this is the surface, it's supposed to be here, and instead it temporarily skips up and starts skipping teeth. That happens sometimes. You need to tension your belt more. Now say it's tensioned properly. It's just going to rip all the teeth off. Not on your pulley, on your belt. The belt is soft rubber. The tensile member is only in the bottom of the belt. It's not in the teeth. It's just going to, if we look at it this way, this area here is just going to rip right off. This is called a shear. Tooth shear. I've done that repeatedly. That happens for smaller belts particularly. If you ever see MXL for a pitch type, don't get it. It sucks. This will happen. Tooth shear. Actually, for a moment, let's just talk about different teeth types. They have every type in the world. They have trapezoidal. They have the kind you have. Look at your belt. You see how it's kind of rounded? Those are called HTD, high torque. I don't know what the D is for. Maybe, I don't know, something. They're high torque belts. The reason they have these different things is for the different amounts of power you're transmitting. Also different types of precision. Turns out trapezoidal, I think, have pretty bad backlash. But anyway, don't worry about that. The last is, the second to last is, say you took your belt and you stretched really hard. You're not even rotating. You're just stretching really hard. You're getting over exuberant and you're tensioning it. You might just rip the tensile members, right? Okay? That's probably not going to happen. It's just not. You'll probably hurt your bearings before you do that. The last and most common is what the gentleman here said, which is fatigue. Who here knows, in the context of mechanical engineering, what fatigue is? Show of hands. Okay. Take your paper clips. Take one of them. Bend it violently back and forth until it heats up and breaks. So I'll do this too. I know, you've all done this as like a freshman experience as mechanical engineering. Summer camp for engineers. Let out your frustrations with Lab 1 on us. Okay, so I'm just going to take my paper clip, twist the hell out of it. Please don't impale your thumbs. Okay, so basically, for those of you who have heard about this, don't go to sleep, you might learn something new. And for those of you who haven't, congratulations. This is actually defeating me. In my defense, my fingers hurt from helping you guys with Lab 1, so it's heating up. It's going to break soon. I'll do it off camera. We'll zoom up. Okay, now take your second one and just bend it just a tiny itty bitty little bit, just enough that you can feel that it moved, and then let go, and it'll spring back. Okay? This is the difference between elastic and plastic deformation. Elastic being it goes back to where it came from. Plastic being it's not going back. Fatigue happens to be different materials. If you deform them repeatedly, over and over for thousands and millions of times, they may crack suddenly. For steel, there's a limit called the fatigue limit. If you tweak it back and forth a billion times below that limit, nothing will happen, ever. You can do it infinitely. If you deform it or put a higher stress on it than it can actually take above the fatigue limit, then it has a finite life, and eventually it will fatigue or crack in half. That's what happens with your paper clip. Aluminum actually does not have that limit, and any amount of stress repeated infinitely will break it in half. This is why airplanes inherently all have to break one day, because they have no fatigue limit. Ah! I made fire. That took way too long. Now the reason this is interesting is because of our belts. If we're using a stainless steel core, they will fatigue. They shouldn't too much. They're along the pitch line, remember? The pitch line is the neutral axis of the belt. That's why it's there. I mean, we can manufacture these however we want. We don't have to put it along the pitch line. Say instead, this is probably how they began, and they, so say this is our belt, that's the flat of it, and then this is our tooth, like that. Hell, we could put it right here in the teeth, right? Well, at the base of the tooth, I suppose. Right there, at the base of the tooth, that's where the tooth begins. We could put it right here, at the very back. Those would all be stupid choices. We want to put it at the pitch line so that we're not fatiguing it. But the tolerances aren't perfect. So we will be seeing fatigue stresses. So let's draw something. I seem to recall from undergraduate, when you go from not being stressed to tension or compression. Okay, so we take a tooth here and we rotate in here. Zero loads here, and then I don't know, depending on which tolerance, say we get some tension or compression here, and then zero loads here on the stainless steel core. That's going from not being stressed to being stressed in one direction to not. Okay? That's bad, but it's not too bad. Now we add another one here, another pulley here, and we go that way. And we're reversing the direction. So now whatever this was, tension or compression, now it's going to be reversed. So let's, for the sake of our example, let's say that the neutral axis tolerance was bad on this. So here we were in tension, and here we were in compression. Everyone see why it's reversing? That's terrible. This will fatigue you way faster. So if you're thinking about twisting your belt and all of this, if there's any way that you can twist it so you keep either all tension or all compression, it will make your belt last longer than if you're weaving in and out tension, compression, tension, compression.
Do you do that by keeping your pulleys on the same side of the belt?
Yeah. So for those of you who didn't hear, you can do that by simply keeping your pulleys on the same side of the belt all the time.
Then that's not.
Yeah. Let's see. So yeah, this would be bad, right? Because it's going around here, say that's compression, and it's reversing tension. So that would be bad. But this is all trade-off, right? So if you're making a robotic prototype for your dissertation, you're not going to see this fatigue. You just want to get it done properly. It needs to last for several years so you can take your data and your experimentation, and the poor dude who follows you can get up on it. But if you're working at a factory, this might be bad. They probably have specifications for that. I've never looked them up. I'm not that interested. But I just want to let you guys know fatigue is one of the most common modes of belt failure here. So I told you about the belt twisting. What time is it? 45. Okay, so let's see what we want to look at. I'm going to go through my outline real quick, make sure I didn't forget anything. Are there any questions that you guys have about belts at this point? Ah, this is awesome. I love this. Sorry, that wasn't an aneurysm finally popping. Okay. I discovered this the other night and almost wet myself with delight. This is so cool. Look at this belt pulley. This is called a helical offset tooth. So this looks pretty similar to the herringbone, but it's different. So these teeth make a V. Anyone know why this is cool? Other than V for Vendetta. Anyone? Huh? Don't need flanges. It wants to self-center. So this is why you use crown. I believe, please don't quote me, I believe this is why you use for flat belts, you use the curve profile. This is called the crowned. That's why you use it for flat belts. I believe that's the corresponding one for timing belts. And I'm going to get my hands on one as soon as I can, and I'll show you guys as a demo in class. That's really cool. So they're pretty rare, but I'm thinking if you could 3D print them, you could do whatever you want, and then you no longer need flanges, which results in much more compact pulleys. Ah, yes, this is the next thing I was going to show you. Okay, so sometimes you need a pulley and they don't have one. How do you make it? Same thing with gears. You need a particular gear, they don't have it, you can't 3D print it because you need it made out of metal. What do? No. You will never make your own gears because it takes very special tooling to do that. And no one I know has that stuff. Even the really good machinists I know can't make their own gears or pulleys. You buy what is called gear stock. Like the stock market. Only legal. Okay, this is what it is. Can you see this at all? So this is gear stock. So they do all of the really tight tolerance machining for you, and then you chop off the little section that you need. There you go, chop that off, and then maybe you'll put some bolt holes in it, maybe you'll put a side set screw. But you have to put flanges. They sell pulley flanges. Stock Drive sells things, it's just bags of pulley flanges. And so that's one of the parts I have here somewhere. Actually, you don't screw them into the side, you mash them into the side. Does anyone look at your... No, that's not. Everyone examine your little pulleys. Does anyone have one with no flanges?
Yes.
That's okay. Can you throw it here? Okay. So this is what's on those two wheels there. I had these machined when I first got here. No flanges, see? Stock Drive sells bags of flanges. So you machine it, and then you take them out and you mash them on there. And then everybody see this? See that little black dot there? What is that? That's a set screw. See how it's in between the teeth? For very coarse pitch pulleys, you can put the set screw directly in the side of the teeth at the bottom of the groove. I haven't had any problems from it. It's a total hack. They don't sell these, you make them. But basically what happened is I took something like this, a long piece of pulley stock. I gave it to my machining friends who couldn't actually make it themselves, but they can chop it and modify it. They chopped it off here. They put a little, God, I hate this thing. They put a set screw in the side, and then I got from it Stock Drive and I mashed the flanges on.
Where do you mash the flanges in?
See these little rims here?
Press fit?
Let's see, what did I do? Sorry, they mashed them on. You can use their special tool which smashes them. In my case, I think I epoxied them with a special epoxy. So they will take if this is looking here, what this is this. We just have a step here. Okay? So now we put a flange around and we hit it with a special kind of hammer here, 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 and here. And it kind of commingles the material. And then that one. Is that one mashed? Yep, this one's mashed. Actually, everybody turn over your pulley. If you have a metal pulley, you see the little divots in the edge of it? On the face? You have divots, I see them.
Oh, these?
That's where they mashed it. Now this is not like a drunk dude with a hammer. This is like a special mashing machine. You can read all about it at Mashables.
I have a question. So you mentioned that you have trapezoidal and like circular teeth. Do you also have involute?
I don't know.
So like if you want
Sure.
to have a gear train continuing into a bed drive, can you have that?
I wouldn't. I'd probably not. I mean, gear teeth are pretty sharp. I wouldn't recommend it. You just want to bolt a gear to a pulley if you want to do that. Okay. Any other questions about belts before I give you the next demo? Is that clock correct? Is it 5:45?
Yes.
Yeah. Okay. Other questions about belts?
Well, you said this the friction drive you use in your car.
Uh-huh.
Can you say something about the difference in terms of torque and power? I don't feel that they are very tensioned.
They're not properly tensioned, and this is an excellent time for this next part. Okay. Let me see here for a second. Okay, everybody take your belt and one pulley. And I want you to, please don't bend the belt very much or it will break. But you're going to kind of try to get it as straight as you can, kind of like this. Right? So just a few teeth are engaged. Don't pinch very hard. Your fingers are small enough radius that it will break it. Okay? Kind of like this. Do you think this will transmit as much torque as if we wrap it all the way around? Like this? No. So this is a very common mistake I've seen with people using belts for the first time, is they don't use as many teeth as they have. We have teeth on the pulley for a reason. We should use them. Okay, if we have two equal pulleys, like this, and then I put a belt around it, how many teeth, or what proportion of the teeth on each pulley am I using? Half. Okay. Now let me make them different sizes. What proportion of the big one am I using? 3/4. Okay, well, around 3/4. And how about on the little one? 1/4. Hardly any. So that's terrible, right? This is just going to shear off. So if you're looking at, everyone know shear is the force over area, and it's usually called tau. Okay, we want to increase this area. The bigger the area, the lower the shear, and then we're not going to shear all of our teeth off. Now say each little tooth here has an area delta A. Okay? So now, and the number of teeth is in, so then this A is the number of teeth in times delta A, the tooth. So we want to bump up the number of teeth engaged so that we're not shearing our teeth off. So what can we do in this case to increase the number of teeth? We can't do that. We've sized the torques we want, and this fits just perfectly for the torques we want. We can't mess with the ratio diameter.
Can we move them apart?
And also, this is constrained in terms of the shaft distance. We can't move them. Idler. Thank you. Idler. Idler. And then in blue, we do that. And then we've increased the number of teeth. This is super ridiculously common. A lot of the times that you see a little pulley and a big pulley,
Doesn't that increase the tension on the belt?
Tension on the belt. Yeah, but that's good because we want a tension anyway. So actually what we can do is we can have this one fixed so it doesn't move and put this one on a slot, and then we're doing a couple things. That looks terrible.
But then that means in your green position, it had to be at least some slack for this to work.
Yeah, exactly. So to put it on, you would have to, so usually what I do, just a quick trick, I make a slot, I put in my CAD, I put my pulley in the middle of the slot, and then I draw my belt here, and then that way, regardless of whether my belt is too big or too small, I can adjust that idler to make it the perfect tension. Okay? If you design it so that your slot only goes one way, so that you can only make it more tight, then that's bad, because you only have one direction you can go. You always want to draw your pulley, your tensioning idler in the middle of the slot. So what we're doing here is we are tensioning the belt, We are allowing for differences in belt length from what we expected, so the manufacturer can be off by a bit and we're still fine. We are increasing the number of teeth in contact here on the little idler, thereby reducing the likelihood that we're going to shear off the teeth there. It's perfect. That's why this is so common. Yeah?
Real quickly, how do you actually make that slot? Like, how do you...
In mill?
So do you just have a screw from behind, like, tightening it?
Yeah. So remember the little track idlers I showed you? The track idler is basically a bearing, and then this is the shaft, and then there's a screw on it. So say this is in a slot, and there's a little, that thing, this is how it sits above the plate. So say this is my plate, this is the slot. Then I can put a nut here. And basically when I want to move it in the slot, I undo the nut, move it to where I want. With the belt tension, I tighten the nut, and then I'm done. It's beautiful. Here's a trick. How do you do this with only one hand? So I have to undo a nut, and then usually there's a little hex hole here where, well, usually the way these work is there's a hex hole up here, and then there's a nut. Now I can't clamp onto here with pliers because I'm going to crunch the bearing and mark up the surface. So I have to put an Allen key here and a pair of pliers here. What's the trick for doing this with only one hand? Put the nut in the slot. There's no reason why we have to size the slot only for the shaft. Let's put the whole nut in the slot. So then if you are looking at it from above, this is going to be hard to draw, but so this is an isometric. God, that's painful. So this is our slot for the shaft, and now let's make a bigger slot here and extrude that up for the nut, and then we'll put the nut in it like that, so the nut can't rotate. So the back of that little slot is essentially our pair of pliers. It's stuff like this that once you learn, your stuff starts assembling quickly. Because if every time you have to have one hand for the Allen key, one hand for the pliers, and then your buddy that you're paying in pizza to slide it for you to keep it tight, that's a pain in the ass. But I can tighten this entire thing with one hand for the Allen key and one hand for the belt just fine. Everybody understand that the hex slot? That's super key. In fact, maybe I should have you do that on the next lab. Okay, other questions about belts? While you're asking, I'm going to go through my thing and make sure we haven't missed anything. So,
what about temperature sensitivity?
No clue. Excellent question. I really don't know. That would be probably something you want to ask the manufacturer. All right, well, we have a little bit of time. So let's talk about I explained to you that belts are a general case, right? Let's talk about cables. Or we can talk about friction drives. Which would you guys rather hear? Nah, let's do cables. We just talked about all this stuff. So I can basically take the steel cable out of that belt and use that as the drive itself. So it no longer has any teeth, but that's okay. Okay. Pass this around. I want everybody to take one dowel and one string. If you are enrolled in the class, because I did not cut more than exactly enough for the class. And while you guys are passing that around, I'll start writing. Remember I talked about friction, and that's how belts work? There's actually a special way of looking at the friction that lets us know how much force we can handle. If I take a pulley and I draw a string around it, okay. If I wrap a piece of string around this, and that's why you have a piece of string in a shaft, this is equal, let's see, hold, I use different terminology. Mu is the coefficient of friction. That's a material property between, well, a match of material properties between the two materials. Theta is in radians that we're subtending this arc. This is that contact right here. So what this is telling us is basically the more wraps around this shaft that we do, the less force it takes us to hold on to that little bit of string, even though we're really pulling on the other end. So those of you who have string, take the string and wrap it once around your shaft and pull. Comes off, right? I mean, without any effort. Now wrap it 3 times. A little harder. Okay? This is really low friction. This is why. This is like, it's the only string I had, so this is what you're getting. But now I want you to wrap it about 20 times. My guess is, at least with mine, I'm literally not holding on to the other end of my string at all. My fingers aren't even touching it. And I cannot pull. This is the beauty of the cable drive. This is one of the beauties. There are many beauties. Typically cables are stainless steel. For stainless steel, on another stainless steel shaft or an aluminum capstan, you only need about 3 to 4 wraps and it will not come off no matter what you do. It's really strong and it's really compact. Now I don't have the demos with me because today's not cable day. Remember we were was everyone able to wrap it around and see that the more wraps you do, the harder it is to pull that other end off? Hopefully. Nodding. It's a long class, it's okay. Remember this? The belt twist? If this is circular, I can do whatever I want. If this is circular, there's no reason why I can't put an arbitrary shaft here and go off at this angle or that angle or that angle. Another one of the beauties of cables is I can reroute however I want. There are a couple exceptions to that. So I brought this here. You're not going to be able to see it much, but let me just briefly show. This is a haptic device I built. So there's a motor down in the middle, and then there's a shaft or a cable that comes up through a series of pulleys, through some hollow shafts, through the center of a differential, up through all this crap. It goes on and on and on. Never in a million years could you do this with a belt. And let me see if I can find it real quick. There we go. Okay, so I know this is almost like shameless self-promotion. So we'll be talking about this on Wednesday. This is a differential, and that's a hollow shaft. My cable comes from a motor down where my mouse is, up around some pulleys, through this hollow shaft, through this series of pulleys, and then up to a bunch of other stuff, which is, see all this? See that cable going through the hollow shaft and around these, where's my mouse? Around the idlers labeled D, around the idlers labeled B, this is the full loop. So my cable comes from a motor here, through some stationary pulleys here and here, through a hollow shaft that is rotating, to the center of a differential. There are 4 idlers here. This entire thing is rotating like this, up through some linear bearings, around an idler, and then back here. You can't do that with a belt. That's crazy.
So let's say you have a situation where you don't want any slipping on the pulley. Could you actually wrap around multiple times on a single pulley?
So that's the problem with belts.
Okay.
You can't.
Why? So
Yeah.
like you would actually go around multiple times
Yeah.
just to get that extra friction.
Yeah. If you could take a belt and keep wrapping it like a cable, it'd be awesome. But belts are inherently limited to less than 360 degrees. Right? If I start here, I can wrap around and maybe say I had infinitely small idlers. I could come in like this, like that, right? I'll never get to 360, but say I had infinitely small idlers, I could. So I get one wrap and one wrap only. It's because I can't do it because I have teeth, and the belts don't like to be twisted like that. But with a cable, if it was just circular, I could do as many wraps as I want. Yeah.
And it won't limit being able to turn it?
It's going to rub up against itself on the shaft.
It kind of self-aligns. If you have too many in a compact space, it will. And everyone I've ever seen starting out with cables, the cable rubs up against itself, and oh my god, I hate cables. And you just have to break it in for like half an hour, just running it back and forth. The cable doesn't want to rub on itself. If it can, it will kind of smooth out. It'll get rid of that. So anyway, that's just a little demo of cables. Next week, we're talking about friction drives. I'm sorry, not next week. Wednesday, we're talking about friction drives. The week after, I believe, we're talking about cables. So just real quick, Lab 2 has not gone out yet, but it's going to be a robot wrist. Just a little bit of a robot wrist. It's just going to be a roll pitch robot wrist, and it's going to be this mechanism here, which is a friction differential. And we're just going to drive those 2 big honking wheels with belts. So it'll be cool. It won't be too hard. It'll be way less work than Lab 1, both in terms of SolidWorks and in terms of prototyping, and it will be more fun. So that's what's coming up. Are there any questions about Lab 1 before we go?
I have a logistics question. The card, the key access that you need, or the card access. So like I went down there today, but they said they hadn't got the forms yet.
Yes. So I have to fill out one last form for them, and then once I submit that, I'll send you an email, and you can do that. Please, yeah, sure. If you need to go, that's fine. Please, everything back in the bin. I need every single belt, pulley, widget, shred of belt, string, all of it. Office hours tonight, starting at 7 p.m. until midnight.
Tomorrow, are there going to be lab times?
Yes. I will post let's do it over here, please. No, sorry. Let's post the office hours in that big bin here, please. I'll post the office hours for tomorrow later tonight. As for what is scheduled right now for office hours, Rob will be in there from 7 p.m. until midnight. If you don't have a Dropbox account, please make one. And then send me the link to your Dropbox. I don't want any USB keys or CDs or DVDs or floppies or ASCII code of your SolidWorks.
Binary.
Yep, no binary.
Printout.
You can just throw them in, I'll organize them.
Actually, I have to ask you. So, if you remember, I need the one thing laser cut. After that, it's just assembly for me, and you said that if it's just assembly, you can come over any time.
Exactly.
So, will you be able to print mine beforehand, or because I booked myself at 9 o'clock?
We'll put you first.
Sorry.
I'll tell Rob to put you first. I'm only going to be there for a little bit. Rob's going to be there most of the night, so I'll ask him to print yours first.
Okay, awesome.
What's up?